we're recording. Okay, and then I'm going to share my screen. There now. Okay, so here's what we are going to do. Before I do anything, I'm going to graph this. So I'm going to go to y equals, and I'm going to clear. And then I'm going to say 7 divided by, and now I have to, because there are 3 terms, whenever there's more than one term, I have to put it in parentheses. So x squared plus 2x minus 3. There. So this is the way I typed this into my calculator. Now, I am going to graph. That is a very, very typical graph of a rational function. And that's what we're doing today. We're starting the whole process of graphing. And the way we start is we talk about the domain, and then from there we start talking about the asymptotes. And today we're going to just talk about the vertical asymptotes and the domain, but tomorrow we're going to talk about the horizontal asymptotes and the x-intercepts and the y-intercepts. So this is what this graph looks like, and we need to keep that in mind. Because, well, you'll see why. I'm going to make this get smaller. And I'm going to look for the domain, which means I only care about the denominator. Whenever that question, you need to restart your computer. Restart later. When you know they'd wait, right? Wait until I'm teaching and then say that. When you're talking about the domain, you only care about the denominator. So what I'm going to do is this. The worst thing that could happen would be to have this fraction 7 over 0. So I need to find out what values of x will cause the denominator to equal 0. And that's what I'm going to do over here. Over here, x squared plus 2x minus 3 equals 0. So x and x. Negative 3 equals 1 times negative 3 and negative 1 times positive 3. What is this 2 business? That's because I already know the answer. I'm going for 2, right? So let's just get rid of that. Stop being fancy. And what I want is for this 3 to equal 3 times negative 1. Because 2 equals 3 plus negative 1. And that's how I know which numbers to use. So I'll use positive 3 and negative 1. And then I'll set each factor equal to 0 and solve for x. What that means is there are two numbers that will make the denominator equal 0. Two values of x. And they are -3 and +1. So I have to take those numbers off the x-axis. -3 and +1. Right, because my factors were +3 and -1. So by the time I set them equal to 0 and solve, the signs have changed. Okay, so -3 and +1 are actually going to become little holes. In the, that's a 4. Here. A hole at -3 and a hole at +1. And what happens then is this. First, I have to write the domain. And so I'm going to write it two ways because the homework problems today sometimes ask you to put it in interval notation and sometimes ask you to put it in set builder notation. So I'm going to do it in both. Okay, set builder notation is the easiest for this. All x such that x doesn't equal -3 and x doesn't equal +1. And this is called set builder or just set. When I was your age and younger, Myra, I learned set notation, not set builder notation. They have changed the name since.
Oh, wow.
Yeah, happens all the time. Drives me crazy. Set no. Nah, I don't think that's good. We'll just say set. Okay, now interval notation is a whole lot more interesting because all of these numbers are okay, and all of these numbers are okay, and all of these numbers are okay. Okay, okay, okay. So all I have to do basically is draw that. That's -3 on the x-axis right here, and this is +1 on the x-axis. So to do that, interval notation, -∞ to -3, the left side of -3, unioned up with the right side of, well, I could do better than that. The right side of -3, right there, to the left side of +1, unioned up with the right side of +1 out to +∞. And all of those numbers in the parentheses are okay. And the bad numbers have been cast out. But we're going to do more with them. We're going to do more with them. Let me erase these parentheses and okays. Okay. It's so important that the graph stay away from wherever x equals -3 or x equals 1. And remember, even if you're up here, x is still equaling -3. Down here, x is equaling -3. Up here, x is equaling 1. And down here, x is equaling 1. So I'm going to draw a vertical line. Actually, I'm not. I'm going to draw a vertical dashed line. Wherever x is -3, and wherever x is +1. These red dashed lines, as some people like you know, and some people don't know, these are the asymptotes, the vertical asymptotes. So this is a vertical asymptote. A, S, Y, M, P, T, O, T, E. And this is a vertical asymptote. Okay, and they go through the numbers that x is not allowed to equal. And they act like walls, preventing the graph from going anywhere. The graphs are never going to cross a vertical asymptote. Okay, and that is why, let me bring back the graph. That's why the graph looks like this. -1, -2, -3. -3 is a vertical asymptote. And see that the graph gets really closer and closer and closer, but it never actually touches. And then over here at +1, we also have a vertical asymptote. And then the graph does this thing. And that's where what we do tomorrow comes in, because notice there is a y-intercept, but there actually is not an x-intercept anywhere. Okay, so all I'm going to do is graph asymptotes today.
Yay!
Yay! Discussion.
I like how you answered my question before I even asked the question, Miss Barbara.
Well, what can I say? But I didn't do one thing I was supposed to do. You see this equation, x equals -3? That's the equation of this vertical asymptote. And this equation right here, x equals 1, That's the equation of the vertical asymptote. Vertical asymptotes have equations, and they always look like this. X equals a number. The numbers that will make the denominator equal 0. So you always start out finding the domain. And here we found the domain because we found the numbers that would make the denominator equal 0. And so wrote it as set builder and as interval notation. And then when we started talking about asymptotes, we noticed that the asymptotes are these lines. Actually, this ends up being the equation of that asymptote, and this ends up being the equation of that asymptote right there. And the graph is graphed in the areas between the asymptotes. And now let's do it again after I save. Okay, we're going to find the domain of this function right here, which means I take the denominator and I set it equal to 0 and I solve for x. But I want to go back to black. X squared minus 100 equals 0. Now 100 is a perfect square, it's 10 squared. So this is x squared minus 10 squared. And that is the difference of squares, and it can be factored as the difference of squares. So I take this x squared and split it apart, x and x, and I take the 10. And I write I write 10, that number, right on the right side of each set of parentheses. So I have an x and a 10 and an x and a 10 in each set of parentheses. And then I put a plus here and I put a minus there. And then I set each factor equal to 0. X plus 10 equals 0. So that x equals negative 10, subtract 10 from both sides. And x minus 10 equals 0. Add 10 to both sides. I didn't cancel them out there either. So that I'll have x equals positive 10. So x equals negative 10 and x equals positive 10. These are the numbers, negative 10 and 10, are the two numbers that will make this denominator equal 0. Now, since this is a fraction, if x equals negative 10 or x equals 10, I'll have 6 over 0, which in real life would mean there's an explosion. So I don't want that to happen. So what I do now is I go to 10 and negative 10. Here's negative 10. And here's positive 10. and I pull them off the x-axis. So now the x-axis has two holes in it. And because I plan to graph, I'm going to put a dashed line where x equals -10 and where x equals 10. And here, okay. And these are vertical asymptotes. And the equation of this one is x equals -10. And the equation of this one is x equals +10. And I didn't write the domain, so let's write the domain right now. Okay. Set builder notation. Squiggle all x such that x does not or cannot equal -10 and x doesn't equal +10. So all you have to do is write your findings right here, but put a slash through the equal sign. Interval notation, of course, is going to be just a little bit different. Let's make the domain green. All of these numbers are okay. All of these numbers are okay. And all of these numbers are okay. And my set build interval notation is going to look like that. In fact, I'm going to write it in green. -infinity to -10, union, other side of -10 to +10, parenthesis, union, other side of +10 to infinity. So these would be the two ways that you would write your domain. And let me there. Let's look at what the graph looks like. So this is 1 over x squared minus 100. We're going to have 1 divided by parentheses x squared minus 100 and close parentheses. So there I have it, and I'm going to graph. Yes, but it's much too big. I am going to reset my window, and I can do that. This is where the window is set right now. So I can go as far to the left as -10 and as far to the right as +10. And as far to the left as far down as -10 and as far up as -10. And there's a space of 1 between each number, like 5, 6, 7, 8. So they're consecutive. I am going to change my window to -25 to 25, -20, oh, nope. Y min, let's try this again, -25 to +25, like that. I'll probably change the scale too, but let's graph now. How ugly. How totally ugly. Right. Second format. I'm going to change this. I did this before because I thought it would be a good thing, but now I can see that it isn't always a good thing. Now, if that isn't ugly, this gives us absolutely no idea what this looks like. I am disappointed. Okay, how about this? -15 to +15. And -15 to +15. Let's see if that's better. It's not. Okay. Well, sometimes it just doesn't graph. However, I am going to make a guess. Let's get rid of this. You don't know this, but the y-intercept is real close to 0, 0, but just a little below it, and there are no x-intercepts. So I believe from little bitty indications I saw over there that the graph is going to look like this. Ooh, but not that wavy. And see, it's really hard. The x-axis is the horizontal asymptote. And it's really hard to draw a horizontal asymptote or even a vertical asymptote because the graph gets infinitely close to the asymptotes but doesn't actually touch it. It does on occasion cross the horizontal asymptote, but never crosses the vertical asymptote. Okay, anyway, that's my guess what it looks like. And the problem is with how amazingly close the graph gets to the asymptotes makes it almost impossible to graph it. truly. Okay, so we will go on. We're not going to let that bother us. We're too tough. Ooh, look at this. That's bad. Let's graph it before we do anything else. Graph. There it is. Okay. So I'm going to go to y equals, and I am going to gladly hit clear. Now, look, you've got two terms in the numerator. We're going to have to use parentheses in the numerator as well. Parenthesis x minus 8. Put it up there. X minus 8 divided by parenthesis 25x squared minus 10x plus 1, close parenthesis. And there we are in y1 equals, at y equals. Okay, I am going to graph this and see what it looks like. Cool. Well, that would lead me to believe there's only one asymptote. Is that possible? Yes, let's find it. Okay. We're going to have to set this equal to 0 and solve. So 25x squared minus 10x plus 1. Okay, A equals 25, B equals negative 10, C equals 1. I have to use the AC method here. Actually, there is a quicker one, but you have to know to look for it. AC is going to be 25 times 1, which is 25. And 25 factors into two numbers that add up to negative 10, well, that's going to be negative 5 times negative 5. Negative 5 times negative 5 equals positive 25. Negative 5 plus negative 5 equals negative 10. So to factor this, and what I'm doing is I'm setting it equal to 0, and I forgot to write that. Because I'm trying to find the values of x that will make the denominator equal 0. And since I have a negative 5, I write it minus 5, and a negative 5, I write it minus 5. So x minus 5 equals 0, and x plus 5 equals 0. I add 5 to both sides. That looks like a 3. Let me... There. Plus 5 plus 5. Negative 5 plus 5 is 0. X equals 0 plus 5 is 5. Then over here to solve for x, I subtract 5 from both sides.
Miss Barb,
Yes.
was it supposed to be a negative 5?
Yes. No. I added 5 to both sides.
Oh no, I mean on the right over here. Wait, I can't really show you. In the parentheses above, if you go above,
Oh, we're not, if this, let me show you, if this were 25x squared minus 1. If that's what it was, then I would have factored this as 5x plus 1 times 5x minus 1. Is that what you mean? But this factors, this gives me two negative 5s. So I'm not going to use plus on one, oh yeah, and minus on the other. It's only minus. Yes, yes. Yes, 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 yes. And so I add 5 to both sides, and what I get is x equals 5. 2 times. Can you imagine?
I have a question.
Yes.
So once you figured out how to factor 25x squared minus 10x plus 1, you got 25x squared minus 5x minus 5x plus 1.
No, I should have. Okay, I was.
And then factor like those two.
No, it's 5x plus 1. You're right. Let us do this with the AC method and we won't mess up. She said, talking about herself.
I'm sorry.
No, no, I agree with you completely. It's supposed to be 1/5. That's the number that has to be knocked off the x-axis. Okay, here we go. I'll have 20, because I came out with 25 equals negative 5 times negative 5. And negative 5 plus negative 5 equals negative 10. I'm going to rewrite it this way. Okay, so I put parentheses. Let me jump down here to do it though. Parentheses around the first two terms. 25x squared minus 5x, and then plus, and I haven't forgotten the minus 5x, negative 5x plus 1 equals 0. Now, over here, we're going to pull out a 5x GCF, and that will leave me 5x minus 1. Because this 5x is also 5x, let me make room for it. (25x squared minus 1 times 5x), so that when I pull out the 5x, I've still got a 1 there. Plus, now, this has not got a GCF, except negative 1. Because your GCF has to be negative when the coefficient of the highest degree term is negative. So this is what we're going to do. We're not going to jump right to it. We are going to rewrite this as negative 1 times 5x plus negative 1 times negative 1, because that's what positive 1 is negative 1 times negative 1. But that's a trick to get us a negative 1 GCF. So I circle the negative 1. Ugh. I'm not going to circle the negative 1. Okay. I'm just going to say there's a negative 1 GCF. And so on my next step down here, I'll have 5x times 5x minus 1 plus negative 1 times 5x plus -1, which is -1, equals 0. Now 5x minus 1 becomes the GCF. 5x minus 1 times the leftovers, 5x plus -1, which is 5x minus 1 equals 0. Yes, indeed. Now we set each factor equal to 0. 5x minus 1 equals 0. 5x, of course, they're exactly the same, so you really only have to do this to one of them. Add 1 to both sides. 5x equals 1, and divide by 5, and divide by 5. X equals positive 1/5. And we'll get the same answer over here. X equals positive 1/5. Now, that's why the graph looks like this. Where is positive 1/5? It's about right there. So, positive 1/5 is about here. And you'll just have to make believe that's a whole. Everything to the left is okay, and everything to the right is okay. And we're going to have just a heck of a time trying to draw an asymptote. But we'll try, because we never give up. I can take this width all the way down to 0.5. Maybe that will work. Don't tell anyone. All right, here we go. Yep, that was the trick. Although it's really hard to do. Okay, now let's look at the graph again. There you go. That's what it looks like. So, we haven't gotten to horizontal asymptotes yet, but the horizontal asymptote is the x-axis. And you've got the graph taking, rising from -infinity, and actually it does cross the x-axis in one place. Even though it's a horizontal asymptote, you can cross a horizontal asymptote as long as it's not too many times, but you can't cross a vertical asymptote at all. So there's my very skinny little vertical asymptote, and you've got the graph rising, rising, rising on both sides of the vertical asymptote. There and there. Thrilling. This is going to have an x-intercept at 8. So what you're going to see is the graph coming up, 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 up. Staying really, really close to the horizontal asymptote until it has to turn. And it probably goes back down like that. I have seen them do that, or it might actually just go like this and stay really, really close on top. Whereas this one, this side, it actually crosses here at -1, and you're going to learn how to do this tomorrow. Oh, good. This is not going to cross the x-axis at all on this side, and it starts coming down, coming closer and closer and closer to the horizontal asymptote, crosses at -8, and gets closer and closer and closer. Ultimately, the graphs get infinitely close without touching to the vertical asymptotes. Sometimes you just have to take that on faith. But this is a good approximation of what the graph would look like. The important thing, oh shoot, the important thing being that when you find the domain, most of the time when you're working with rational functions, you're going to find values of x that make the denominator equal 0. Well, whenever you've got the denominator equaling 0, that's undefined, very bad. So you have to make sure x never equals those points, which means those points are not in the domain. The vertical asymptotes go through those numbers that are not in the domain. There is one complication to that, and we are going to get to it later, but not yet. So for now, you can just make a rule that vertical asymptotes always go through the numbers that make the denominator equal 0, because most of the time they do. Here, I didn't even draw it, but it looked really interesting. Yeah, let's graph this again, because this was really interesting. Okay, y equals clear. Okay, this is just the number 7, so I don't have to put parentheses around it. 7 divided by, I do have to put parentheses around the denominator because it has 3 separate terms in it. X squared plus 2x minus 3. And now I'm going to graph it. That's what it looks like. Is that cool? You've got asymptotes, vertical asymptotes at x equals -3, going all the way up and down, and at x equals 1, all the way up, all the way down. And the graph is drawn in 3 separate segments. Okay. I didn't mean to turn it off again, but let me save this. All right, now we've gone from finding the domain to actually setting out to find the vertices, the vertical asymptotes. See, that's what the instructions say. Find the vertical asymptote. Okay, fine. But I have to start the same way. I have to take the denominator, 1 minus x, and set it equal to 0, and solve for x. I'll be left with a 1 on the left and an x on the right. So when you say 1 equals x, that's the same thing as saying x equals 1. Well, that is the number that makes the denominator equal 0. So that's the number that has to be taken out of the domain, because x cannot equal 1, or you would have 1 minus 1, which is 0. What would you have? If x equaled 1, you would have 1 minus 3, which is negative 2, over 1 minus 1, which is 0. That's not defined. Okay, it's undefined. What if you weren't defined? I can't even begin to comprehend that. But a fraction, yeah, okay. So we are going to take x equals 1 out of the domain. Here's 1, and I'm going to make a hole right there. Okay, goodbye 1. Now, in set builder notation, which is what we were doing before, you would write the domain as, even though this isn't asking for the domain, I'm doing exactly the same thing in all of these problems, which is, okay, writing the domain, all x such that x does not equal 1. And that's what your domain would be in set builder notation. In interval notation, you're going to imagine all of these numbers are okay, and they are. All of these numbers down here. And all of these numbers over here. All of the numbers on both sides of 1, but not 1. So your interval notation is going to be the interval from negative infinity to the left side of 1, unioned up with all the numbers on the right side of 1, going all the way to infinity. It's like you jump over 1, and you put a U there instead. Now, as for your vertical asymptote, here it is, right here. Now, we can look at the graph. and see what it looks like. This is just informational. If you don't like working with calculators, if you're not good at it, if you feel like they're just too alien, you don't need to. It just really helps to get a view of what you're dealing with so you can get a mental image. So that's what we're doing right now. Parentheses, x minus 3, x minus 3, divided by parentheses, 1 minus x, parentheses. And I'm going to move this over a little, and I'm going to graph. That's what it looks like. Very, very typical. Notice they're like mirror images of each other on both sides, on either side of the vertical asymptote, which goes up and down. You have to imagine it being there. It's not really there. Okay. But that's where the asymptote is. Now it says determine the vertical asymptotes. Well, I have to find the domain first. Okay. And now you're going to find out the exception. I had kind of hoped I could wait, but I can't wait. So we're going to do it now. Time. Yes, we have time too. Almost all the time. Almost all the time. Like the first 4 problems, it was always true that you take the denominator, set it equal to 0, solve for x. The 2 numbers you get as your solutions are going to be the bad boys that need to be taken out of the domain and replaced, if you want to think of it that way, with a vertical asymptote, because these 2 numbers are taken out of the domain. Here, negative 10 and 10 were taken out of the domain. Here, 1/5 was taken out of the domain. And here, x equals 1 was taken out of the domain. Did we graph that? Yes, we did. And it was like that and like that. Okay. Now you've got a rule in your mind. Whatever numbers you take out of your domain, they're going to be vertical asymptotes. But it's not always true, and we are going to deal with that right now. Okay. Now, the first question is always, what is the domain? I have to take the denominator, set it equal to 0, and solve for x. So, yeah, well, okay, wrong color. 2x to the third minus 1x squared minus 21x. All 3 terms have an x in it, have at least one x in each term. Excuse me. So I'm going to pull out the x as my common factor. That leaves us 2x squared. I didn't need that one after all. Minus x minus 21. Okay, now I'm going to factor this. A is 2. B is negative 1. I did need the 1. B is negative 1. And C is negative 21. A times C, 2 times negative 21 is negative 42. Now 42 is 6 times 7, right?
Yes.
That means, thank you, that means it's going to be negative 6 times positive 7, or positive 6 times negative 7, because to get a negative number, you have to multiply a negative times a positive, or a positive times a negative, different signs. Okay, so now we are looking for two numbers that we can add together and get the B number, which is negative 1. Well, if I add 6 and negative 7 together, I will get negative 1. So don't forget your X there, but we are going to take what's inside the parentheses, 2x squared, and then minus 21, and that minus x is going to is going to split into 6x minus 7x. It's still negative 1x. But now I will put parentheses around the first two terms. I'm going to erase my negative sign and move it closer, because I need a plus here. And then put parentheses around the second two terms. Now the first set of parentheses is going to be fairly easy to factor by GCF. We're going to have 2 times, I want to do it in black. 2 times x plus 2 times 3 times x. Both terms contain a 2 and an x. So 2x is going to be my GCF of the first two terms. Okay, a 2 and an x are gone. I have an x left over. And then pulled out a 2 and an x, I have a 3. Now, here's the difficult one, of course. The highest degree term has a negative coefficient, which means our GCF, our greatest common factor, has to be negative. So, I'm going to write this as negative 7x. Negative 21 is going to be a positive times a negative. In order to get a negative 7 out of it, I'm going to have to take plus 3 and multiply it by negative 7. And so that's how what's on the inside breaks down. Negative 7x plus 3 times negative 7. So I can pull out the negative 7. That will leave me an x and a plus and a 3. Now x plus 3 becomes the GCF, so I write it x plus 3. And then I write the leftovers, which are 2x plus negative 7, which is 2x minus 7. Meanwhile, I've been leaving out the equals 0. Equals 0. Equals 0. I can't do that, because up here we have a factor of x, and then we have a factor of 2x squared minus 1x minus 21. So the best thing to do would have been this. Now that we've figured out the AC part, I'm going to go ahead and get rid of this so I have room. You'll see why I'm going to do it, because this is a step I should have taken and didn't do it. I have two factors here, the one in parentheses and the x out front. I set each of them equal to 0. Then I do the AC stuff on here. All right, x equals 0, you can't do anything to x. So, yeah, you're going to do your AC stuff. That's what I'm going to call it. Do the AC stuff. And then we came out with this. So now here we are at x plus 3 times 2x minus 7 equals 0. I let x plus 3 equals 0 and 2x minus 7 equal 0. I subtract 3 from both sides over here. And so 3 minus 3 is 0. I will have x equals negative 3. And over here, I will add 7 to both sides. Divide by 2 and divide by 2. X equals 7 over 2. Now, 7 over 2 is 3 halves, 3.5, just in case you're wondering. Now, the reason I did this is you need to know where on the x-axis it's located. So now, let us pick up where we left off. Here's what we've got. We've got x equals 0 from up here. We've got x equals negative 3. And we've got x equals 7 over 2. And we'll just keep it our secret about the 3.5. Now, before I can say definitely what my vertical asymptotes are, I have to do something I did not tell you about before because it wasn't relevant, and now it is. We have to go back up here and completely factor the top and the bottom. We're going to have x times x times x over x times x plus 3 times 2x minus 7. From which we get, in another color, how about blue, from which we get x equals 0, x equals negative 3, and x equals 7 over 2. Now we're all set to have 3 vertical asymptotes. But then something happens. This x and this x cancel. Leaving us with x squared over x plus 3 times 2x minus 7. So now we're down to 2 vertical asymptotes. Again, in blue, x equals -3 is the equation of that vertical asymptote, and x equals 7 over 2 is the equation of this vertical asymptote. So, before we do anything else, this is 3. 3.5 is here. You're going to have a hole there with a vertical asymptote going through it. And that's 7 over 2. -3 is right here. You're going to have a hole here with a vertical asymptote going through it. Okay, so I'm going to take the easy way out. Okay, so you've only got 2 vertical asymptotes. But let's look at the domain. The domain, yeah, still doesn't have an x equals 0 in it, because that would make the original denominator equal 0. Just imagine putting a 0 in for every x. Back before this was factored. So you still can't use x equals 0. It's just not bad enough to be a vertical asymptote anymore. So let's see what this graph looks like. We're going to have x to the 3rd power. There it is, right there. And I have to hit the right arrow key to come down. Divided by parentheses, 2x to the 3rd I had to hit the right arrow key to come down and continue, minus x squared minus 21x. Okay, so 2x squared minus x squared, 2x to the 3rd minus 20x minus x squared minus 21x. Okay, there we are. I am going to hit graph. That's what it looks like. Notice you only have 2 breaks in your graph. Actually, there is a 3rd one that doesn't show. So judging from this, we're going to have, okay.
Wouldn't the other be hard for you? But wouldn't the other one be where x equals 0?
No, it wouldn't be, surprisingly, because x canceled out over here. We still have to honor the fact that 0 is not in the domain, but it no longer is going to be a vertical asymptote. So this is what I'm going to show you. Where was I? Okay. You come up from being really close to the asymptote. Now, you don't know this yet, but x equals 0 would have been the x-intercept, but we're not allowed to use it. So there's actually a hole there that's called a point of discontinuity. That's what happens when you cancel out a factor of the denominator. This was a factor in the denominator, and it canceled out. So now it becomes what's called a hole. It becomes a hole, but not a vertical asymptote. So let me go back and just, okay. Gets closer and closer and closer to the horizontal asymptote. And on the rarest of occasions, it can cross a horizontal asymptote. Tomorrow we find the horizontal asymptotes and the x-intercepts and the y-intercept. But today you've got to take what I say about that. It's really true. It's really true. Most of the time you would have 3 vertical asymptotes if that x had not canceled. But it did. So now you've got a hole in the graph. In the blue graph, you've got a hole.
Miss Barbara?
Yes.
I guess what I'm a little confused about is why wouldn't we graph 7 over 2? Because
Here it is. This is 7 over 2. 3.5 is 7 over 2.
Oh no. Okay.
Yeah, this is the equation of that vertical asymptote is x equals 7 over 2, or x equals 3.5.
Okay, I didn't see very clearly then because I thought it was at 3 and I was like, wait, where's the 3.5? Got it. Just kidding.
Yeah, and here's x equals -3. These are the equations of the vertical asymptotes. Meanwhile, you've got a hole here at 0, 0. So these things can get pretty complicated. But we're going to do more tomorrow. You'll be experts by the time we're through tomorrow. Okay.
Sounds perfect.
Okay, now I'm going to hang around for anybody who might have questions. After I save my document.
Have a nice day.
Oh yes, I will. You too. And have this terrible feeling I went to the wrong place to save it. Not that that's a terrible thing.
No.
Let me look. No, it's in the right place.
Yay!
All right, that's good. That's good. I wish I could draw better. I have never, ever been good at drawing.
You did an amazing job. What are you talking about?
I did an amazingly bad job.
No.
Oh well, oh well. Before I start castigating myself, I should stop recording. Yes, stop recording right now.